Okay, so the fundamental theorem of calculus, the bane of my existence as far as Math 31 goes. This one is really heavy. Hopefully you guys watched the Khan Academy video already, because I think he says this better than I can. It's not that I can't use it, but if somebody, I don't know, some university prof somewhere asked me to explain this to the level of detail that Sal on Khan Academy can, I just can't. So I figure, why not use what's out there as far as resources? Here is like the heavy theory stuff, right? So this is the jargon out of the textbook. And so what I really need you guys to understand is what Sal got to in the video, okay? If you do the derivative of an integral from some lower boundary a, doesn't matter to what it is, to x of some function f at t, basically you can plug that x in for that t and it becomes f of x, okay? The other thing that we need to understand that's part of this theory is that if we do the integral under some curve, so we have something like this, if we do the integral from a to b, then if we take all of what's under b and subtract all of what's under a, right, and then those things will go to the left forever. What we're left with is the area under that curve from a to b. So if we take the antiderivative at b, subtract the antiderivative at a, that gets rid of everything over here, so we're left with that. Okay, so this is kind of part 2 of the fundamental theorem of calculus, sometimes it refers to. So in the textbook questions, some of them are saying use the second part, blah, blah, blah. This is what they're talking about. So you're doing essentially the antiderivative plugging in b minus the antiderivative plugging in a. That's what we've been doing, right? So we did that in 6.3. That was like, we're going to do from, I guess I should put in numbers, from 1 to 3 of 3x squared dx, right? We would say the antiderivative of this is not 3. The antiderivative of this is x cubed, and we're going to evaluate it from 1 to 3. So then we had 3 cubed minus 1 cubed, right? F at b, the upper one, minus f at a. So that's what we've been doing. That's just now referred to as the second part of the fundamental theorem of calculus, okay? So we'll do some examples. We're not going to do the whole note package this time, just because a lot of this is beyond what you guys need to know for a non-AP level. Okay, so if we want to find the derivative of the integral from negative pi to x, remember that it doesn't matter what this value is. If we have an x up here, and then this is represented in terms of t, that just means we're sticking that t in there. Okay, so the easiest way to do this is just say, okay, this is just cos of x. Okay, as a proof, and we won't do this every time, but as a proof, we can do this using the antiderivatives. So using antiderivatives, we can confirm for ourselves that this does in fact work. So if we just do the integral first, so we're going to do the derivative of whatever we come up with for the integral. So if we're just looking at that, we're saying, okay, if I need to do the antiderivative of this, think of what did I do the derivative of to get cos, that would be sine. Okay, or I guess, sorry, this is a t still because this is a t. So sine t. And we want to evaluate that from negative pi to x. Okay, so then we're going to be doing the derivative, and we're going to leave that part till the end, of sine x, that upper boundary, minus sine of negative pi, that lower boundary. So we're going to do the derivative of sine x. We can't replace with anything yet, but we can figure out what the sine of negative pi is. Negative pi is over here, right? If we go negative a full pi. So the sine at this point, remember this point has coordinates -1, 0. So the sine of negative pi is 0. So then we're just doing the derivative of sine x. We know that the derivative of sine x is cos x, okay? So that's a much more complicated way to do this, right? We could prove it to ourselves because cos x or cos t is an easy enough thing to take the antiderivative of. But there's cases where that's not true, and so we just say, okay, I'm just going to use the fundamental theorem of calculus. If it's from some numerical value to x, I'm going to plug that in, we're gold, okay? So for this one, we want to find dy dx, so we want to find the derivative of this. That means we're doing the derivative with respect to x of this whole thing. So from -2 to x of the square root 1 plus e to the 5t dt. Okay, so because this is just some numerical value a, we're going to x. Basically, that just means we're plugging in the x wherever we see it as a t. So this is going to be the root of 1 plus e to the 5x, and that is our function. Okay, so we've done the derivative of the integral. If we run into cases where the upper limit isn't x, then we have to use the stuff that we've been talking about earlier in this unit. So because we have x on the bottom and 7 on the top, remember that if we want to switch the boundaries of our integral, then we just have to make that whole thing a negative. So then all of this can stay the same. And now we're doing the derivative of this thing. So I'm just going to move my equal sign. Sophie, sorry if you're doing this in pen. We're doing the derivative of this thing. If we're doing the derivative of an integral, remember that we're just going to plug in an x, that upper boundary, every time we see a t. Okay? And then this negative is just going to move out in front, because if we have a negative derivative or a derivative of a negative, it's like basically like 2 times 3 is the same as 3 times 2. Okay, so that negative is going to go out in front. We're going to have 2x to the 4 plus x plus 1. And there is our function. Okay, if the upper limit can't be expressed as x, we need to apply the chain rule. So basically we're going to do the derivative of the upper boundary. So we don't need to do like a chain rule for the whole dang thing. We just need to multiply by the derivative of whatever that upper boundary is. Okay, so if we use, for this one, if we use antiderivatives, we'll prove it to ourselves. We're going to be doing the derivative of the integral from 1 to x squared of cos t dt. That is the same as the derivative of, now if we look at this, if we want to integrate from 1 to x squared of cos, what must we have done the derivative of? It must have been sine. There's our antiderivative, and that's t, and we're going to evaluate it from 1 to x squared. Then we're going to do sine of x squared minus sine of 1. So, the derivative of this, we want to simplify this first. And this is x squared. I should put that in brackets, because it's not sine squared x, it's sine of x squared. So the derivative of this guy is going to be, we're going to use the chain rule. So the derivative of sine is cos of x squared, and then multiplied by what's in there, the derivative of that, so 2x. And then the derivative of sine of 1. Sine of 1 is just a number. We can plug that into our calculator, it would spit out a decimal. So the derivative of that number is a 0. So we're going to write this as 2x cos squared. Okay, so then if we use the fundamental theorem of calculus with the chain rule, it is much easier. So dy dx is going to be equal to, we're just taking that x squared now and putting it in. So it's going to be cos of x squared, and then multiplied by the derivative of that upper boundary, 2x. Much easier, same result. Okay, so again, we're not doing like the chain rule of the whole thing. We're just going to multiply by the derivative of that upper boundary. Okay, so this time, instead of doing it both ways, because this is a really difficult antiderivative, I don't want to do that. That sounds awful. So we're going to just do using the fundamental theorem with the chain rule. So dy dx is going to be equal to, so we're doing the derivative of this whole thing. So d dx of this whole thing oops. So notice how it doesn't really matter if it's u's or t's or same difference, okay? We're just sticking this upper boundary in wherever it has a u, in this case, right? It just has to match whatever's out here. So this is going to be the root of 1 plus 5x squared over 5x. And then we need to multiply this by the derivative of that upper boundary. So, oh my gosh, 5. Okay, so 5 divided by 5, those are going to cancel. So we're going to end up with 1 plus, I'm going to distribute this, so 25x squared over x. Okay, this next one is too complicated. Get rid of it. Notice how this is not a number, so we're going to not worry about that in this course. And then these ones as well are more of an AP application, so we'll get rid of those. And we're going to go down to halfway and say evaluate the integral. Check our answers with that function integration on your calculators. And we're going to use the integral evaluation part of the theorem, so like part 2, which is that part I talked about at the start of the video. So we're taking the antiderivative of b and subtracting the antiderivative of a. So what we've been doing, okay? So this is going to be, this is basically what we were doing in 6.3. We're just practicing it. I'm going to rewrite this as the integral from 0 to 1 of x squared plus x to the 1/2. I find integrals are easier when we have exponents instead of roots. So if we need to think about, okay, what must our function have been for our derivative to be x squared? Well, it must have started as an x cubed, and since there's a constant of 1, there must have been a 1/3, so that when the 3 came down, 3 multiplied with 1/3 gives us the 1, and then the exponent dropping by 1 gives us 2, okay? And then plus, same deal here. So if the exponent ended up as 1/2, it must have started as a 3/2, okay? And then we have to think about what coefficient goes here to make it a 1. So if the 3/2 came down and multiplied with something to form a 1, basically it has to be the reciprocal of that something, because 3 times 2 would give us 6, 2 times 3 would give us 6, and those guys would cancel. Okay, and then 3/2 minus 1, it gives us 1/2. So there's our function, and we're going to evaluate it from 0 to 1. So we're going to take this, and we're going to plug in our upper boundary first. And then subtract our lower boundary, and it's nice. Notice how I gave us really easy numbers to plug in, because I don't know what like 4 to the 3/2 is, but I know what 1 is, because 1 times itself any number of times is still just 1. Okay, so 1 cubed times 1/3 is just 1/3. 1 to the 3/2 is 1, plus 2/3 is 2/3. And then all of this is just a 0, right? Because 0 times anything is 0. So 1/3 plus 2/3 is 3/3, so this answer is just 1. And we can check that on our calculators. This one, again, I'm going to write it as a negative exponent because I find that easier to deal with. So -2 to -1 are my boundaries on my integral. I'm going to write this 2 x to the -2 dx. So remember that 2 can come out in front. So then we have the integral of x to the -2 dx with the 2 multiplier out in front. It just makes it easier. Okay, so then we need to think about, okay, if my exponent ended up at -2, it must have started at -1. And then that -1 would have come down, multiplied in front with something to give us a positive 1. So if a -1 multiplies with something to give us a positive 1, this must have been a negative to start. And then we're going to evaluate that from -2 to -1. Okay, and that 2 is just going to multiply that whole thing. So it's going to be 2 and then -1 to the -1. Or we could have wrote this as 2. Maybe that's easier. Let's get rid of this. So this is -1 over x. So it's going to be -1 over -1 minus gosh, it's confusing, minus -1 over -2. So there's all sorts of negatives in here. So -1 times divided by -1, that's a positive 1. So 1. And then this is negative times negative is a positive, negative, so this is still a negative. So 1 minus 1/2 is 1/2, and then 2 times 1/2 gives us 1. These numbers aren't that bad. These ones, I'm not going to worry about. We haven't gotten here yet. This one, I'm going to show you, yeah, you may as well do this one. So what I did here is this looks super complicated, but if we manipulate this formula a little bit, it's actually not that bad. So if we go from 0 to 4, if we split this into 2 separate fractions, because this is 1 over root u minus root u over root u, which we could change into, this is 1 over root u, so this would be root u to the -1. Remember, root is a 1/2, so this would be u to the -1/2 if we simplify it. And then this is just a 1. So now, oh, I forgot the du. Now, this actually isn't that hard to do an integral of, or sorry, an antiderivative of. So we're going to do the antiderivative of this. So if it ends up at -1/2, it must have started as a positive 1/2. And then that -1/2 would have dropped down and multiplied, and it turned into a 1, so it must have been a -2 to start. And then the integral of -1 would have been the antiderivative of -1 would have been -u, right? And then we're going to evaluate that from 0 to 4. So -2 times 4 to the 1/2 minus 4 minus -2, 0 to the 1/2 minus 0. I don't know, I added an extra bracket. But this, remember that 4 to the 1/2 is the same thing as a square root. So this is going to be root 4, so 2. So 2 times 2 is 4. This turns into -8. And then this whole thing is 0, so we get -8. Okay. The rest of this, you also don't need to worry about it. So for practice, I want you to do page 306 numbers 1, 3, 5, 9, 14, 21, 29, and 31. And 33. There was one more on the original list, but I decided to not do it. So these ones are the ones that I want you to do. Okay? If you have any questions, let me know.